Okay, this is heat and mass transfer, homework 1, part A. So let's get right into it. So to begin, I will explain how transport phenomena, those being heat, momentum, and mass, how each of their fluxes are related by multiplying their respective gradients by diffusivity. So let's start by defining flux. So flux is the flow of a physical property. So physical property just being any measurable property, such as temperature, pressure. The flow of a physical property through a surface over time. So mathematically, what that looks like would be something like flux equals the physical property over units of area and seconds. So let's start with heat flux, because we know heat flux of conduction as Fourier's law. Okay, and so what we're looking for here is some value like the flux equals that gradient times diffusivity. In that diffusivity being in units of meter squared over second. Okay, so we know Fourier's law as such. Heat flux is equal to the negative thermal conductivity of a material times the change in temperature over change in position. Now, what does this mean? The thermal conductivity of a material describes its willingness to change temperature, or its resistance to a change in temperature through conduction. So, writing each of these terms in SI units, we find that our heat flux is in units of joules over meter squared seconds. And that's equal to the negative thermal conductivity, which we know to be in units of joules over meter times Kelvin times second. So relating that change in energy to throughout the distance surface and the temperature over in time. Our change in temperature and change of position could just be denoted as a change in Kelvin over change in meter. Okay, so knowing that our flux, which in this case heat flux, as these Q quotation marks, will be the gradient times diffusivity. We know that the change in temperature over change of position will be our temperature gradient. So, meaning our thermal conductivity should be in units of meter squared over seconds, as stated by the problem statement. So, how can we get there? Well, the answer would just be to cancel as many SI units as possible. So, using heat, we could divide our thermal conductivity term by our heat capacity. So our heat capacity is in SI units of joules over kilogram Kelvin. This is because heat capacity describes describes how much energy an object requires in order to raise its temperature. So, with our new equation, we find heat flux. Now, if we don't change the heat flux term and we multiply our we divide our thermal conductivity term by our heat capacity, then we must also multiply our temperature gradient by the heat capacity. So we'll get our heat flux equals negative thermal conductivity divided by our heat capacity times our heat capacity change in temperature over change in position. Okay, so our updated SI units look like this. Heat flux remains the same. Our diffusivity term with the thermal conductivity now divided by our heat capacity will we'll have joules in the denominator and meters, Kelvin, seconds, which is given by our thermal conductivity. Now that we're dividing by our heat capacity, we should multiply by its reciprocal in SI units. So we'll get joules in the denominator, kilograms, Kelvin in the numerator. Now, again, we need to get to these meters squared per second. So we're not quite there yet. What else could we do? We could again divide by another unit. We'll use density, which describes an object's mass over a given volume. And we'll use SI units of kilograms over meters cubed. This will help us eliminate these kilograms and get a meter second in there. Meter squared. Okay, so, and once again, if we want to keep our heat flux term the same, we should multiply our gradient term by this density. So, our updated equation looks like this. Heat flux equals negative thermal conductivity divided by heat capacity times density times heat capacity, density, change in temperature over change in position. Screen is getting really blue. Anyway, continuing on to ignore the blue screen. This leaves us with the following SI units. Heat flux remains the same. With our thermal conductivity term, we once again find joules in the numerator, meters, Kelvin, seconds in the denominator, and then we'll multiply by the reciprocal of our heat capacity SI units. So that'll add joules in the denominator and kilogram Kelvin in the numerator. And then we'll multiply by the reciprocal SI units of our density. So that'll give us meters cubed in the numerator in kilograms in the denominator. This will then be multiplied by our heat capacity density, change in pressure, change in temperature over change in position. So what that will look like is kilograms from density in the numerator, meters cubed in the denominator. From our heat capacity, we'll get joules in the numerator, and then kilograms Kelvin in the denominator. And then from our change in temperature, we will get, what color did I use? Yellow. We will get Kelvin in the numerator and meters in the denominator. Okay, so now our favorite part. We get to cancel our units. Okay, looking at our diffusivity term, we cancel joules, kilograms, Kelvin, meters gone, squared, and then our gradient term, cancel kilograms, Kelvin, we'll end up with joules, meters cubed. So this will be a physical property over a volume. In this case, meters cubed our volume. That will denote a concentration. So this term ultimately is our energy concentration, as it's in joules, and also describes the rate at which our heat diffuses throughout the system. Simplifying this term, we'll end up with negative meters squared over seconds, which is perfect. That's exactly what we're looking for up here. So this term describes the rate at which heat diffuses throughout the surface. So it's effectively our heat diffusivity, which gives us our flux times our diffusivity times flux equals our diffusivity times our respective gradient, in this case temperature. So now we'll move on to our momentum flux. And to define our momentum flux, we will use the shear stress equation, which can be written as so. Shear stress, or tau, is equal to viscosity, or mu, times the shear rate, delta. Now, we'll try to relate this shear stress equation to our heat flux equation. So essentially, our shear stress is pretty much like our heat flux. Our viscosity term will be like our thermal diffusivity, or it'll end up being our momentum diffusivity. Let me write thermal here. It'll end up being our momentum diffusivity, just like our thermal conductivity ended up being our thermal diffusivity. And the shear rate, shear rate is analogous to the temperature gradient. So that's the change in temperature over change in position. So shear rate can be described as an object's sort of resistance to moving when like smearing against another object, if you will. So basically that could be written as change in velocity over change in position. So we'll keep our mu term the same, and our shear stress we know as force over area. Okay, so in the momentum equation, because this isn't related to heat, we will only multiply by our density this time. Density being, again, mass over volume. So the SI units will be kilograms over meters cubed. Okay, so basically what we'll get in our updated equation will be something like this. Our shear stress, or force over area, equals mu over density times our change in velocity over change in position times density. Now, this term right here is, here, I'll just write it over here. Viscosity over density, that describes an object's kinematic viscosity, which is just the resistance to flow, which is good because that's a lot like our thermal diffusivity term. Thermal conductivity term in our heat flux equation. So, writing out all of our SI units, we find force being mass times acceleration, we'll get kilograms over kilogram meter per second squared times our area, meter squared, equals SI units for viscosity are kilograms over meter seconds, and then the reciprocal of our density will give us kilograms in the denominator and volume in the numerator. And then multiply all of that by change in, what color did I use before? Yellow. Change in velocity over change in position. So velocity being meter per second, and our position just being SI units of meters, which cancel out to 1 over s, which is good because we know our units for shear rate is just in a per second basis. And then we'll multiply that by our SI units for density. So kilograms in the numerator, meters cubed in the denominator. Okay, so going back to our Physics 1 knowledge, we know that our momentum is written as mass times velocity. And if we break that down into its SI units, we'll get kilogram meters per second, which is this term right here. And so that term is basically just our momentum and divided by a volume, which is just going to be our momentum concentration, similar to our energy concentration above. Now, this term, which is just going to be our diffusivity, will cancel kilograms, cancel meter, the denominator, and squared in the numerator, and lo and behold, we get our meter squared second, just like our thermal diffusivity, but this time it is our momentum diffusivity. Our third and final transport phenomena is mass transfer. Now, to define mass flux, we'll use Fick's law, which states as follows. The molar flux, J, is equal to the negative diffusion coefficient, which is just going to be found experimentally and vary from material to material, times the change in concentration over change of position. So this is like both the momentum and heat flux equations that we found. The J is similar to Q and heat flux, and the shear stress in the momentum equation. The diffusion coefficient, as the name suggests, is just like the other two diffusion terms. Momentum diffusivity being the viscosity, and the thermal diffusivity being the thermal conductivity. And then our change in concentration over change in position, that is our concentration gradient. Let me write that in. Now, that is similar to our shear rate in our momentum equation and our temperature gradient in the heat flux equation. And simply enough, the SI units for the mass flux equation will just be similar to above. So just like our heat flux is in terms of joules over meters squared seconds, we find the physical property for the mass flux is moles over meter squared seconds, star through the surface over time, and that is equal to negative of our diffusion coefficient, which, believe it or not, is in our favorite meter squared second units, and then our concentration gradient, concentration being the change, concentration being moles over a volume. So moles over meter cubed times meters, because that's just our change in position. And that'll be our mass flux. Okay, now I will explain Fourier's law. So, Fourier's law, as I stated before, describes heat flux. And can be written as follows. Heat flux equals the negative thermal conductivity times the temperature gradient. So change in temperature over change in position. Now, let's start with this negative sign. Temperature, according to thermodynamics, will flow from, or heat will flow from areas of high temperature to low temp. So this means that even if, so here, let's draw a graph. That was a bad line. That's a bad one too. Third time's the charm. It's decent. Not great. But anyway. Temperature, position. So, say we have 2 points, A and B. And as we move further along the axis, our temperature increases. This would leave us with a positive slope and a positive temperature gradient, because temperature gradient will increase with the slope. Despite this, our heat fluxes should be negative because, again, heat will move from areas of high temperature. So point A has a higher temperature than point B to a low temperature. So it'll move in the opposite direction, meaning that we would have to counteract this by giving that thermal conductivity a negative sign. This even works if, for example, we start with high temperature, and as we move down the axis, we reach a lower temperature. So, in this case, the temperature gradient is decreasing, which would give us a negative value. But as heat is, again, higher temperature over here, lower temperature here. So that should be a positive value. So that negative on the thermal conductivity would multiply by the negative temperature gradient and result in a positive value. So now breaking down these terms and what they really mean. So our heat flux is in units. Like I said earlier, flux describes the flow of a physical property through a surface over time. So in our case, with Fourier's law and heat flux, that physical property is energy and is measured in joules. And that is over that, through that surface, so area, meter squared, throughout some time, seconds. That equals our negative thermal conductivity, which describes a object's resistance to transfer heat. And like we said before, this is in units of joules per meters Kelvin second. Oops. Now, that is, the energy having to overcome meter seconds Kelvin. You get the idea. But regardless, I'm tired, bro. Now let's break down these terms. So, as I stated before, our flux describes a physical property through a surface over time. So in the case of heat flux, our physical property is energy, measured in joules. And that will be through a given surface, so area, meter squared, times a time, seconds. This flux is equal to our negative thermal conductivity, which is in units of joules over meter Kelvin seconds. And it's in these units because our thermal conductivity describes an object's resistance to heat transfer. So however much energy, joules, the object has, divided by the distance, temperature, and time will be that thermal conductivity. That term is then multiplied by our temperature gradient, which, like I said before, is just our change in temperature, kelvins, over our position, meters. Okay. When we divided this thermal conductivity term by units of density and heat capacity, we got our thermal diffusivity. So like before, K divided by rho C, we'll get our joules times meters cubed times kilogram Kelvin all over over our joules, or we'll start with meters times Kelvin times seconds times kilograms times joules, which results in our meter squared seconds. Now, the difference between our thermal diffusivity and our thermal conductivity is that our thermal conductivity describes the object's resistance to that heat transfer. And as mentioned before, the heat flux, which is just our diffusivity times our gradient, describes the flow of that physical property across over a surface. So in this case, this thermal conductivity is multiplied by our temperature or energy concentration. So it is just the change in energy throughout the surface over time, whereas this thermal conductivity term is really more so just to represent the change in energy of an object. So that diffusivity term, including the time and area.